Okay, so let's move on to continue to talk about section 2.5 continuity. As we discussed in the first part, uh, when we claim that fx it is continuous at x equals c, then we must have the condition limit as x approaches c, f of x equals f of c. Okay, so that's the key for supporting continuous at a point. Okay, and we also talked about a lot of discontinuity names, right? The removable discontinuity, jump discontinuity, and also the infinite discontinuity, right? And also how to check whether a function it is continuous at a point or not. Okay, so now let's move on to talking about more about the continuity. In fact, in the second part, guys, I hope you can have again the idea about this. You don't have to memorize all of this. Okay, I think it is important to support your future calculus courses. So I'm gonna present it here. So here, let's talk about properties of continuous function here. So suppose we have two functions, and those two functions they are both continuous at x equals c. Okay, and here's the conclusion here. If you make the summation or the subtraction, let's see fx plus g of x or fx minus g of x, and then this new function will also continuous at x equals c. Okay. Meanwhile, if you multiply those two functions, they're going to give you a new function. For example, let's maybe talk about something like this. Fx equals x squared. Let's see, gx equals, I don't know, like an x. And, these two functions, actually they're both continuous on all numbers, okay? Assume, I don't know, let's see, set c equals 1. Pretty sure that this is a polynomial. It is continuous at x equals 1. G of x is a straight line. It's also continuous at 1. Okay. As you can tell, guys, you do the multiplication that is going to give you its x cubed. It's going to be still continuous at x equals 1. Okay. Now you can also construct the quotient fx over g of x, and also make sure that g of c is not 0. Okay, so this new function, the quotient format, is also continuous at x equals c. Okay, and also, if you multiply a constant to any of these functions, let's see, k times f of x, this function it is also continuous at x equals c. Okay, so we can also do the power. So f of x raised to a power n, and also make sure that n is a positive integer. So this function is also continuous at x equals c. Okay, and last one, the nth root. Okay, if you have an nth root of fx, and provided that this function it is defined, okay, on an interval containing the number c, and then also this n is a positive integer. Also, we can get as a conclusion the nth root of f of x it is continuous at x equals c. So to sum up for this part, you have two functions that are continuous no matter like the basic operation plus minus multiplication division raised to power, and they take the nth root. It basically the continuous still holds. Okay, so that's the first part about the properties of the continuous function. Now let's move on to the other parts. So for here, we're gonna talk about inverse function first. So it says like this: if we have a function, that function it is continuous, okay, and at the same time, that function also has an inverse function. Let's see, this is f inverse, okay, and then we can see that the inverse function it is also continuous on its own domain, okay. So simply speaking, if you have a function, it is continuous, and it also has an inverse. The inverse function is also continuous on its own domain. So a very quick example, I assume a lot of us already know this part, is the natural exponential function and the natural logarithmic function. They are inverse functions of each other. As we can tell that this is a graph for f of x equals natural exponential e to the power of x, and this dashed line is equals y equals x. This curve stands for the inverse function, which is natural logarithm function. As you can see, exponential it is continuous. The natural logarithm is also continuous, right? And also, do you still remember that one of the properties about the inverse function is the graph, it is symmetric with respect to y equals x, right? So you can think about this y equals x is a mirror. So you lift, you flip, you're gonna get this, okay? So inverse function continuous, okay? Also, this part is called the composite function continuity, okay? Continuity. So I think I just did. There's a typo here, and this is called the G composite of f, okay, or G of f of x, okay. So this is the notation for composite function, and believe it or not, in chapter 3, when we're starting to talk about how to take the derivative of a given function, composite function gonna play a key role for supporting the chain rule, okay, which is one of the most powerful derivative technique in all the calculus series, okay, all the calculus series. It's such a big, important part. So, first of all, if you still remember something about the format of composite function, great. If not, that's okay. After you watch this video, maybe just Google what is composite function, and then make sure that you know how do we define the composite function, okay? So here's what we're gonna see here. Composite function and continuous. Suppose I have a number c here, and I know that a function f of x, it is continuous at a c, okay? It is continuous at a c. And if it's continuous at a c, definitely f of c, it's defined and exists, right? That's part of the condition to support a continuous at a point. And meanwhile, another function g, it is continuous at f of c. In other words, guys, this is input, this is output. The meaning of the composite function is let the output from one function as the input of the other function, okay? So the output of fx is the input of g of x, and g of x, it is continuous at f of c, so which gives us is g of f of c, okay? Then, what we can tell is g of f of x, it is continuous at x equals c, okay? So that's the composite function continuous, okay? So we know fx is continuous at c, good. Now we know g is continuous at f of c, good. And then the composite function g of f of x, it is continuous at x equals c, okay? So composite function and continuous. Last part, the intermediate value theorem, okay? And it described into this way. If we have a function that is continuous on a closed interval, let's say from a to b, like this graph, from a to b, okay? What it said is, okay, if y is 0, okay, it's some value, is a value between f of a and f of b, okay? I draw a y value here. Then there must exist at least a number c on the interval from a to b, such that y of 0 equals f of c. okay, equals f of c, right? So you can see that from this graph, this is very, very clear, right? So you take any values, right, from between fa to fb, and then correspondingly, there's gonna be a value of c on this interval, and f of c equals this y of 0. That's a brief idea about the intermediate value theorem. And what this is used for, I can give you one example here, okay guys, because I think this part is important. Suppose, I don't know, so we have a graph, something like this, okay? So let's see if we have f of x. You know, one of the key part for numerical method is to find the zeros of a given function. In other words, suppose this is a, okay? We know f of a equals 0, right? Which is the x coordinate, which is the x-intercept. But often, if this function is too complicated, we might not be able to solve it explicitly, right? So how do we solve it numerically? Well, intermediate value theorem starting to play the role here. Now let's think about it into this way here, guys. Suppose this is, I don't know, this is 1. Let's say this is C5, okay? Suppose A equals, this is 2 here, okay? Now, believe it or not, do you agree that f of 1 in our problem here, it's less than 0, right? And also f of 5 is greater than 0, agree, right? My function is continuous from 1 to 5, and also those two endpoints f values have opposite sign. One is negative, one is positive. So do you see that actually 0 is between those two endpoints, right? Then I can make the conclusion, well, there gonna have at least 1 0 for my function f of x, okay? So this is one of the direct application about how to locate make a good location to find the zeros for this function. And some of you might think about, okay, once we got this, how do we keep continuing to find a better or more accurate position for this zeros? Well, I can tell you one of the brief ideas, guys, is you can think about it into this way. If I have this interval, okay, in other words, I take the half of those, and you can see that. So this is gonna be 3, right? This is gonna be 3. So you can still evaluate f of y is negative, and then f of 3, do you agree, is positive? So do you see that, guys, with this new condition here, I actually can shrink my interval to make the location more precise compared to the previous one. Meaning, I can guarantee that between 1 and 3, there's gonna be a 0 for my function. So this part I already get rid of, right? So do you see that? And then you can use the same idea to half that. And actually, 2 is a middle point between 1 and 3. When you evaluate f of 2, and then that's gonna give you a 0. Okay, so this is one of the very basic algorithm, the bisection algorithm in numerical analysis. And the whole idea of why this is true is from the intermediate value theorem. Okay, so this is the end of 2.5 continuity, and I hope you enjoy this. I'll stop here, and I'll see you soon. Okay.